Okay, let us talk about multiparticle states. First of all, let's remember what are the spaces, the typical spaces in which states in different theories that we have looked at so far live. Classical mechanics, for now, has states that are positions in momenta, and they live in a six-dimensional vector space called the phase space, as we said, right? So Q and P themselves are observables, and we have X, Y, Z components in Q and P, so there's a six-dimensional space per particle, six-dimensional vector for each particle, and then we can have multi-particle states also in classical mechanics. But the space they are occupying is the so-called phase space. Now in quantum mechanics, we have states, we denote them typically in this brand cat notation, often called with Greek letters as well, and they occupy a different type of space. It's also a vector space, but it has infinite dimensions, not just six. This space is called the Hilbert space. Here we also know that the observables are expectation values of some emission operators um, that are wedged between the states, and this gives us the physical observables. Typical observables are also have a probabilistic nature, and quantum mechanics is deeply non-deterministic, as a contrary to classical mechanics. Now, moving on to the quantum field theory world, we have states that live in a generalization again of the Hilbert space. It is the so-called Fock space. So formally, the Fock space is a direct sum of tensor products of single particle Hilbert spaces, right? So you can think of it as this formal sum that is written as the zeroth power, that is just a complex, that is just a number, plus the Hilbert space of a single particle plus the tensor product of a state of two particles with a symmetry factor, which we talk about later, plus h times h times h. Yeah, the tensor product of a three particle state, and so on up to infinity. You could have in principle infinitely many particles occupying a multi-particle state. So formal the definition of the Fock space is this sum of the tensor products, which just generalizes the existence of um, not just one particle, but many particle states. And as we said in the very beginning of this course, in quantum field theory, um, particle number is not a conserved quantity necessarily. We can create and annihilate particles, so states that have many particles are not uh, necessarily evolving and conserve this particle number, but change. So they would states with a defined number of particles could jump from one representation to the other, having 5 particles, then becoming a state with 4 particles or 3 particles, and so on. Yes. So just to mention what the basic observables are that we are actually going to construct in the future, those are so-called amplitudes. Yeah, amplitudes are essentially um, so-called transition matrix elements that, if you square them, give us a probability for transition from an initial into a final state. But we will discuss uh, these questions of time evolution a bit later. But the fundamental building blocks that we're actually going to look at are transition, these kind of elements that describe transitions from some state to another state, and their overlap. We have used A and A dagger to describe the fields phi. In fact, yeah, A dagger and A can be thought as a creation and annihilation operators of particles with a certain momentum p. Yeah, now we can actually ask a question. If we specify the momentum p, what about the position of this particle q? Yeah, If you remember the uncertainty principle, delta P delta Q, bigger than some value, well, in our units, bigger 1. Yeah, so if P is well defined and we use it to label a state, delta P tends to 0. Yeah? So that also means at the same time that delta Q has to go to 1 on delta P and it has to go to infinity. So that means that the state with a well-defined momentum is completely delocalized in space. Yeah, but this is something we don't really worry too much about in quantum field theory because we are interested in changes in the momentum vectors. But that again, on the philosophy of how to construct the observable of those states, we will discuss in the future lecture. For now, we want to construct states in the same way as we were doing for the harmonic oscillator. Yeah, that is also something that you did in question 1 of sheet 2. We want to construct states by application of the creation and annihilation operators. First of all, the annihilation operator annihilates the vacuum, also here, for any p. Yeah, the vacuum state is by definition an empty state here. The norm of the vacuum state, on the other hand, is 1. Yeah? We define it to be normalized. Now, the single particle state is very similar. This is very similar to the harmonic oscillator that we saw, is the application of the creation operator to the vacuum with a certain prefactor. This is the only difference with this. The existence of this prefactor we will show why it is necessary in a relativistic theory. We can figure out the normalization of this state by multiplying p and another state p prime. We still use the creation and annihilation operators here to do that. And we can rewrite a dagger as a dagger A plus the commutator of a dagger, right? Because the commutator is a dagger minus a dagger A. So if we were to write it out, this would cancel this term and we would be back at that one. So we can formally write it down as a flip of this operators plus the commutator. And then we know that here we have the annihilation operator that will hit the vacuum state and gives us 0. So this term is gone. And the other state is the vacuum expectation value, so-called vacuum expectation value of the commutator between A and A dagger for P prime and P. Vacuum expectation, we can define all kinds of expectation values, but the particularly important one is the expectation value between vacuum states that we will hear a lot, the vacuum expectation value. All right, but we can just evaluate it because the commutator here is just a complex number, or just a number, actually, a real number in this. In this case, it is actually a distribution, the delta distribution. Still, it is a number that we can pull out in between the states, and the vacuum state normalization, we can use it, and it's 1. So we know that in the end of the day, with these prefactors, we have this delta function in three-dimensional space that will force P to be P prime, the momenta. And that lets us actually rewrite this square root factor as just 2 times EP times this delta function, because here P had to be set to P prime. Now let us look at the 2 particle states. They're actually very simple, or very similar. If we have a state with P1 and P2, we just have to apply a dagger P1, a dagger P2 to the vacuum, and would have the appropriate relativistic factors up here. We create 2 particles from the vacuum, in other words. Now, an important mention here is that indeed the commutator of 2 particles with different momentum is actually 0. So we can flip the position of the particles, so P1, P2 can be exchanged to be P2, P1 by just flipping the order of the commutators here, and the state will be the same. So permuting 2 particles for this type of particles that we are studying now doesn't change the sign of the wave function. This is called the Bose symmetry. Those particles are called bosons. We will discuss the implications of this symmetry a bit later. But for now, we just will state the fact that the norm of this state is very similar, where we still have the product of EP1 and EP2, and here we have the products of delta functions that set P1 equal to P1 prime and P2 equal to P2 prime, or a permutation of that, P1 setting it to P2 prime or P2 being equal to P1 prime. This is also a possible combination because it comes from the fact that we can shuffle around the creation and annihilation operators. And to show this expression, this will be a question on exercise sheet 3. This is in principle a simple exercise of just using the properties of the commutation relations. The commutation relations of the creation and the annihilation operators. Then we can also use the property that we can write this expectation value of a dagger between two states by flipping it around and taking the Hermitian conjugate of the operator, and this will be just the complex conjugate of that expectation value. So if we have the vacuum hitting a state, the norm of the vacuum and the state with a p, with the back momentum p, we can write it like this, the creation operator, then take its complex conjugate and see that now we have a annihilation operator hitting the vacuum, and that gives us 0. So the expectation value of any state with the vacuum itself is always 0. And similarly, we could check that if we have three different vectors like p, p1, p2, the expectation value of them would be 0. In particular, because you have different numbers of states, of particles in the states, and then the expectation value here would be always 0. This allows us now to generalize it to the n-particle state, the whole idea. We simply apply n creation operators to the vacuum and have n relativistic factors up front here. The norm is 0 if the number of particles is not equal. This should be m and n. So if the number of particles is not equal, this norm is always 0. Otherwise, if n and m is equal, we can have, or we will have, the norm being the sum of delta functions, as we saw in the two-particle case, with permutations that we will have a product of delta functions that is summed over with all possible permutations. Just as an example, let's go up here. So the product of those two delta functions, where we have P1 being combined with P1 prime and P2 with P2 prime, or P1 with P2 prime and P2 with P1 prime. So these are two possible permutations, two elements of the sum with different products of the delta functions. And this is exactly the formula here, where we just write it in the compact notation. These delta functions with permutations are multiplied and then summed over all possibilities how we can permute the terms. And in general, the wave function is symmetric under the permutation of particles. This is a quite interesting phenomenon that I wanted to discuss now. So, principle, if we have a state with two particles and the sign doesn't change when I flip them, so in principle you could have the same particles, or the particles being in the same quantum state, and the state would be still a valid physical state, right? So you could say them to be equal, you flip the sign, we get the same state. Now, just as a contrary, imagine another type of particles that we will encounter much later in the course, but they are called the fermions, or particles that satisfy the Fermi symmetry. Here, by flipping the two particles in the state, we get a minus sign in front of the wave function. So now what would happen if we set P1 and P2 in this case, right? So P1 and P2 is equal to minus um, P1 and P2. If they are equal, we have a state with two particles that supposedly live in the same state, P and P, equals to minus P and P. Yeah. So a number that is equal to its negative is uniquely defined to be zero. Yeah? So this state vanishes and doesn't exist. So fermions cannot exist in um, in the same or cannot occupy the same quantum state. This is a phenomenon that you know from atomic physics, for example, where we have electrons that sit in orbitals and they can only be paired in up and down pairs, and then they have to occupy the next orbital and the next, and so on. So fermions are good building blocks of matter, if you wish, because like little Lego bricks, they can be stacked. They don't want to sit in the same place. You can't really make them and force them to sit in the same position, having exactly the same labels. Okay, but bosons are different. Bosons don't care. They are very you know social, let's say. Bosons can be pushed to arbitrary numbers in a single quantum state, and I just wanted to mention some examples of bosons that we know from in nature, or bosonic states with high occupation numbers. So one example would be the laser, right? They have a lot of photons in a given state and are essentially coherent light wave, and that gives them the power. There's a lot of photons that um, can hit the target having the same wavelength, same energy, and excite very narrow lines and atoms, and all those applications that lasers are good for come really from the fact that we have all the photons. Photons are bosons, by the way, that occupy the same quantum state. There are also other bosons, for example, atoms with spin 0, spin 1, that can form uh, coherent matter waves. So they can be also cooled down and then become have basically a unified wave function that is very compact, very cold, and they also can have very unusual properties. Yeah, those things are so called the Bose-Einstein condensates. Then finally, a related phenomenon are superconductors, which are similar to a Bose-Einstein condensate, but here we have effective degrees of freedom where electrons that are actually fermions with spin 1/2 form pairs. Yeah, you can essentially say E and E with spins 1/2 and 1/2 forms an effective state that is phi with spin 0. And this is a pair in momentum space, but however, that doesn't really matter for now. The main thing is that they are um, able to occupy the same low-lying quantum state. And this, in fact, if you work it out in the full QFT picture of this interaction, gives us conduction that happens without resistance or energy loss while they communicate in their in in their momentum space and can basically create a current without any friction and energy loss. So this makes them a superconductor, based on so-called pairs of electrons and making the electrons effectively into bosonic pairs called Cooper pairs. Cooper pairs. Yeah. Another effect in a superconductor is that the electric field is actually screened. That means that the photon, the carrier of the electromagnetic interaction, gets a mass. Yeah? That means that the electromagnetic field inside a superconductor decays as e to the minus m. The m gamma is the induced mass of the photon times r. So if you have a superconductor that goes like this, the electric field quickly drops. The final phenomenon I wanted to mention is the so-called Higgs field. And that Higgs field gives a mass to force carriers of the electroweak force. And in fact, we live in the superconductor phase of the weak force because the Higgs induces in the same way the effective mass for the so-called W and Z bosons that are the bosons and the force carriers of the electroweak force, and gives them a substantial mass of 100, roughly 100 proton masses, 100 G, or order of magnitude 100 GeV, which makes the force act on distances that are of the order of 1 divided by 100 GeV. That is, as you could say, 10 to the minus 2, 1 on GeV, and this is 10 to the minus 2 RP. So it's like 100 times shorter than the proton mass. So it's a very, or the proton size. So it's a very short-ranged force that only operates inside nuclei and is perceived as weak, even though the factual constant of its coupling, or the coupling constant, is fairly larger than the electromagnetic one. The force of the field seems very weak because it's very short-ranged, exactly because of this mass of the gauge bosons of their mediators, and that is induced by this superconductor type effect of the Higgs field that is all ubiquitous in our space. So that's some very interesting examples of, um, of bosonic physics.